So we've seen a variety of graphs: polynomials, exponential, logarithmic, trigonometric, etc. Now what we're going to do is we're going to combine those functions. We can take two totally different functions and add them together, subtract them, multiply them, divide them, and get whole new interesting graphs. So here's an example. Let's call some function f of x, we'll say that it's sine of x, and some other function g of x, exponential function 2 to the x. If I add these two functions together, of course, that would be the equation. I simply add them together, subtracting them, multiplying them, dividing them. Several things that we can do with these. What would the graphs look like? Well, that's a bit tricky. The easiest way to go about doing that is to generate a few points on each of these graphs and then add the points, or subtract the points, or multiply or divide. So I've done one example. If I take these two graphs and add them together, f plus g at x, well, I've generated just a few points. They're not very nice because both of these graphs get a lot of decimals and fractions. So sine evaluated at -3 is that, at -2, at -1, etc. I evaluated the exponential function 2 to the x at those same values for x. So the input is the same into both of these. And then to get the new y-coordinate for the sum of those two functions, I add the y-coordinates together. So if I add this to this, I get the new y-coordinate. So since f of x contained the point -3, -0.14, and since g of x contained the point -3, 1/8, adding those two together, I get a new point on the sum, -3, -0.015. So taking a few values, down here I've sketched the graph of sine of x, our sine wave. I've sketched the graph of 2 to the x, and then in blue, I tried my best at sketching what the sum of those two graphs would look like. So what would happen is these negative values added to these small positive values get bumped up a little bit. This y-intercept stayed put because 1 plus 0 is still 1. And what's happening here is all of these points got much higher. If I'm adding these larger numbers, they all became much higher, and the graph to continue kind of like that. The best way to do these, in fact, is to use graphing software or a graphing calculator. Then you can get a better idea of what the graphs look like. It's very difficult to sketch these. So when we combine two functions, we want to know what the new domain is of that combined function. If you know the domain of the graphs that you started with that you're combining, we say that the domain of their combination is the intersection of the two. All that means is where they overlap. An example here, I've drawn the graph of log of x and this radical function, this square root function here. Remember that the domain of log of x is greater than 0. It always stays positive. And this is your square root function reflected and shifted 5 to the right, so that the domain of this graph is x must be less than or equal to 5. If I combine these two functions, their domain would be all real numbers such that x is greater than 0, but less than or equal to 5. When we do quotients of functions, there's one extra thing you need to keep in mind. Because you'll have a denominator, you're dividing by some function, you have to make sure that the second function, what I called g of x, never equals to 0. We always do that with rational functions, make sure the denominator doesn't equal to 0. So again, an example, I've decided to take log of x and divide it by x minus 3. The domain of this, once again, is greater than 0. The domain of a line, again, is all real numbers. No restrictions on this function on its own, but because it's in the denominator, I have to make sure it never equals to 0. So we add one more restriction, x cannot be 3. So the intersection of their two domains is x is greater than 0. And then we add this extra restriction, x cannot be 3, because we want to make sure the denominator never equals to 3. So composite functions are when we want to plug some function into another function. The notation is like this, f at g of x. That means f at g of x. It means we're plugging the function g of x into the function f. So we say this is the inner function and this is the outer function. So the one that comes second is going to go into the one that comes first. So as an example, I've got this equation f of x equals x plus 3, and this square root g of x equals square root of x. So f at g of x means I'm going to take g of x and plug it into f. Here's g of x, root x, and where I have an x in this function, I'm replacing it with g of x. So I'm taking the function f and replacing it with that function, root x, the end result is root x plus 3. Where I used to have an x, I've replaced it with the other function. The other way around, g at f of x means take f of x, plug it into g. Take this linear equation, plug it into the x in there. So we're finding g evaluated at f of x, g evaluated at x plus 3, taking that, putting it in the square root, root x plus 3. In terms of domain, the domain of the composite function is simply the domain of the function that gets plugged into the other one, the inner one. So if we're finding f at g of x, the domain of this is the domain of g of x. If we think of functions as sort of machines where we input something and output something else, this composite function, f at g of x, means take x, run it through g of x, the inner function, you get an output, run that through f of x, and you get your final output, this function inside of that one. So some applications require combinations of functions. So here, for instance, I have an exponential function and subtracting a linear function. Here I've evaluated the function at 3, the function at 4, so I get an idea perhaps of what it looks like. I could generate some points and make a sketch of this guy. But let's say, for example, I wanted to know when this equals to 0, going the other way around. What value of x makes that 0? Try to solve that here. Problem is, if I bring the x over there, I'm nowhere closer to solving this equation. It's very, very tricky. The algebra is difficult. We haven't seen anything like it. Logarithms wouldn't do the trick. Nothing that we've seen would do the trick. So we're kind of stuck with just graphing each of these and finding where they intersect. So this is the line y equals to x. This is the exponential function 2 to the x minus 3. I've sketched these graphs over here. So the line y equals to x goes straight up through the origin, 1, 1, 2, 2, 3, 3, etc. And the exponential graph, 2 to the x minus 3, is simply an exponential graph shifted 3 units to the right. You can see from my sketch that they intersect twice. They're going to intersect somewhere in this area, and they'll intersect again somewhere in that area. We can sort of estimate where that is, but the reality is the best way to do this would be to use graphing software, plot the two, then you'd be able to tell very easily from looking at the graph where the point of intersection is. And in fact, plenty of software will actually tell you where the point of intersection of two graphs are.